Hello and welcome back to Real-Time Rendering here on the Lötwig Fusel channel. Today we're going to talk about deferred rendering, or how do we bring all information that we have learned the last videos together into a concept that works very well on our GPU for multiple light sources, for multiple type of materials, for kind of like all of the glory that real-time rendering gives us, so that we have kind of like a good base system on which we can easily expand. Alright, so I already told you we're talking about deferred rendering, but before we can actually go into the details of what deferred rendering is, we first gonna need to talk about a bit about forward rendering, so what is kind of like the classical way of doing it. After we can talk about deferred rendering. So let's get started with forward. And yes, I know this game has a photo mode, but well, sometimes it's just easier to hit the Steam hotkey. So alright, forward rendering. Why the hell is this GeForce overlay now there? Just go away. Dude, go away. Do I actually need to? Yeah, it's like not updating. Alright, so what is forward rendering? So forward rendering basically means a single pass for geometry and lighting. So last video we kind of like talked about the lighting, how we light our scene. And the video before we talked about geometry, and in forward rendering we just take these two pieces of information together and do this all at once. So transform our geometry and then do our lighting. This is kind of like the straight forward way of rendering, but we of course have an issue there. If this would be kind of like the ultimate thing, we could just use forward rendering for everything. The issue is we are coupled to the light, but let me actually go a bit into detail there to explain you what we are doing. So basically we have one single pass there, which is our full rendering of the three-dimensional object. So first we start by geometry transformation. So we take each vertex, so for each vertex we kind of like apply all of our transforms, so our world transform, our camera transform, and our perspective transform, view transform. And after we have done this for kind of like all vertices, we can rasterize this, or better to say, the GPU is gonna rasterize these triangles down to pixel base, and then we do pixel shading for each pixel. But the issue is that in case we actually wanna do this like in one single pass, so everything at once, we kind of like need to accumulate for all lights. So we need to actually, in one invocation of the pixel shader, for example, we would need to handle all of our lights. Or we could use some other techniques to actually go over that and maybe make this a bit easier. So kind of like the most straightforward way would be to take a for loop, and for each light in our scene do light computation, sum the result together and done. Issue with that is that dynamic branching and stuff like that is not that good on the GPU. The GPU doesn't like kind of like this way of programming. Branching is not good because like the GPU is built for doing massive parallel processing, and if you have too many kind of like branches, especially when the materials in the objects get smaller, you actually get some issues there, because like you have different materials and you need to evaluate different stuff, and then you could kind of like go against the rule of the GPU for having the same program for many threads, because like they go on different paths, they're kind of like having different branch conditions, and this could become an issue. It actually works well for not many lights, but as more the lights are getting, that many more lights you have in the scene, and even through it as much versatile lights you have. So if you have kind of like several area lights, several spotlights, point lights, so different light types. If you have different light types and you have several of them, so in case your artists get very detailed on doing this, for example with like illuminating surfaces and stuff like that, image-based lighting, and if you have like several of these lighting techniques, then you kind of like get limited, because you need to do like everything in this one single shader, which leads to the problem of Uber shaders. So you kind of like have one shader that does everything, and this is not good. I mean, it's good because we don't need to do some mode switching on the GPU, but because we have like that many branches, we at some point get limited by our shader, because, well, we can like say we support like 8 lights for each light type, and then there's just a single for loop. In case the light does not contribute, we just kind of like make our equation so that it returns 0, so we kind of like just input some default values that will always result in a contribution of 0 for each color channel. And yeah, but the issue would be that you still kind of like iterate over each light. I mean, the casts are calculatable, but the system is not very flexible, so you kind of like have some issue there. You could kind of like avoid this by dispatching a draw call for every light object combination. So in case you kind of like have a, say, let's say this giraffe here, and you have 5 lights, you would draw this giraffe 5 times, and you would, for each time you draw this giraffe, you would, for example, just evaluate like 1 light. Or you could, for example, write a shader for your point lights, a shader for your spotlights, and draw for each of these kind of like light types the giraffe once again. The issue with that, of course, is that you always do the geometry transform again. So you kind of like always fire up the whole rendering pipeline, even through your just going to shade an object, and this is also not good. It also has some other issues. It's not just kind of like how you organize these lights and how you organize these lights and object coupling. It's also some other topics like decals. For example, if you want to do decals basically are surface modifications to existing geometries. So for example, you would have several textures, for example, for some mold, or just some other special effect, or bullet holes, so kind of like some additional stuff that you may actually want to do procedural, or that you want to kind of like apply manually after the scene has kind of like been designed. So you kind of like design the wall clean, and then you add some dirt decals, mold decals, to kind of like put some variation in there. So you just build some basic tiling, and then you just combine and blend over several more kind of like inputs. And of course, like these inputs, these decals need to be calculated as well. I mean, you could in theory bake them, but you may actually wanna opt in for doing them as a separate rendering pass, because like the user could also switch them off if he kind of like doesn't want these decals. Or what you could also like do is like dynamical decals, so if kind of like the mold generates over time, so it's getting more, so you could like apply the mold a bit more, or even generate this procedural, for example, in a compute shade, and then overlay it. So kind of like just layering several stuff together, which is basically modifying the surface. I mean, like forward shading does allow decals, but they are a bit harder. I mean, you could just paint another color on them, but if you want to actually influence how stuff is being computed, for example, if you have like a bullet hole which kind of like is scratching the metal that is hitting, so you kind of like want to subtract the metalness of the material, and you want to actually increase, for example, the roughness, so that it kind of like looks worn because this bullet has shot in there. Then you kind of like need to also modify the surface parameters, but in case you have forward rendering, they were already rendered, so you would need to make 100% opaque decals that do not alter the underlying values, but that are kind of like replacing them with new values. And on deferred rendering, you actually have the opportunity to actually alter values to, for example, say this mold is just gonna make this a bit more reflective, so it's kind of like, yeah, some imperfections there like in the material itself, so you can kind of like do a bit more if you're doing the decals with deferred rendering. And of course, decals on forward rendering are harder, because for each decal rendering pass you would need to evaluate each light again, because like the decal is maybe also lit by the scene, so you need to compute lights there as well, and then you kind of like go back to this infinite loop up here where you need to optimize the system that it fits again for decals, which is a bit brute force. Alright, so what is the good solution to all of that? The solution is deferred rendering. I mean, it's not like the golden solution that you throw to any like issue. I mean, there may be still the case that you want to do like forward rendering, for example, if you want to archive maybe a bit higher frame rates, and you have kind of like a more like dedicated scene. For example, if you're building a like first-person shooter game which is competitive, you may actually want to kind of like build your lighting around like some very basic and just a few lights there, so that you kind of like can say, okay, I always have a maximum of 8 lights there, so I can just do a for loop over 8 lights, and I'm just having like one skylight, so I hard code the skylight, I have ambient light, I hard code the ambient light, for example, just a bit of ambient, for example, and then you say I have like these a maximum of 8 dynamic lights, so I always write a for loop over each of these 8 lights, and this could, especially if in case these are so low count of lights, can be more performant than deferred rendering, and you don't need that much memory, because deferred rendering is eating up quite a lot of memory and also bandwidth, so you would kind of like, on such of a competitive game that should run on several platforms and consoles at a high frame rate, you may actually want to opt for forward rendering, because you can run it on better hardware and you can archive higher frame rates, so you don't need like the latest GPU, the latest RTX 3090 two-way SLI group to kind of like run the game at 165 FPS. So you would kind of like make this a bit more limited in your rendering to also allow like lower tier hardware to run at higher frame rates, because your game may be competitive. But in case you are doing like a single player story game, or just a game that is just wanting to have such a beauty like all these modern story games have, where you kind of like have your ray traced reflections, where you have all your like real-time rendering gloriness, you want to go and actually opt in for deferred rendering. This should run on like every console out there today, so I'm talking about Xbox One and PlayStation 4 upwards, and on modern PCs as well. So deferred rendering should be, in case we want to do some real-time rendering here, should be the kind of like, or not real-time rendering, like beautiful looking real-time rendering. So deferred rendering would be our way of choice, so we would actually opt in for doing that. Actually, there is something that's kind of like in between, which is I've forgotten how it's exactly called, but there's a kind of like a hybrid version between these two versions, where it's kind of like decoupled but not decoupled, which may also be a solution, but we're gonna go for a fully deferred rendering system here. So, talking about that beautiful deferred rendering, what is deferred rendering? Deferred rendering basically decouples geometry and light. So you have a separate path for your geometry and a separate path for your light. Of course, these paths need to communicate with them. So basically, this is done by storing the geometry and texture. So intermediate textures, intermediate render targets. So basically, your first pass just writes some data of the surface to a texture. And then in a next step, this information is inputted or read from, and then used for lighting, for the shading process itself. And this is very nice, because you decouple the geometry path from the light, and this is actually the main purpose that deferred rendering tries to archive. So what is the first pass? The first pass is a geometry pass. So of course, again, we're gonna transform the geometry, and as I already told you, we are extracting surface properties. So for example, material IDs, colors, roughness, object IDs, normal directions of the single points. Base color, already told that, like maybe metalness and several other things, like anything you actually want. So kind of like you are the designer of your default rendering system, you store everything you need for your rendering engine. And you store all these to intermediate render target, not to a intermediate render target, to multiple intermediate render targets. This is also why like graphic pipelines and APIs like DirectX support 8 render targets at the same time. So you would be able to actually store 8 times 4 floating point values. So you would have like 32 floating point values at the maximum that you can store, which should be sufficient for any system. And of course, always remember, each of the intermediate render targets do cost some memory. I mean, like most of the time you want to have them at full resolution, but there may be actually some use cases where you can actually like decrease your resolution, for example, to a half. So if you're just doing some mouse picking, this would maybe not be required to be pixel perfect. So mouse picking is basically when you click on the pixel, you kind of like read back the texture that has been rendered and take a look on this texture, most of the time like just a UN32, so it's 32-bit unsigned integer inside a single texture, and you just take a look at the specific value at the location where the user has clicked, and you get an ID, and this ID corresponds to an object in your scene hierarchy, and then you can kind of like look up on which object the user has clicked. And for example, this may not be required to be pixel accurate, because like the user will not be able to actually aim the mouse to a single pixel, so you would maybe actually come away with that term, making it a half of a screen resolution to actually spare memory. And yeah, so at some points you actually may want to reduce the resolution of these intermediate buffers, but basically on like a regular basis, at least for shading, where you do computations on a per pixel base, all your intermediate render targets will actually need to be the same size as your output size, or basically your render size. So if you have the solution like DLSS or like the AMD, I don't know the name, it's not like very recent from AMD, like the upscaling solutions, then you would of course do all these computations at this upscaling at this pre-upscaling resolution, and then feed the final image into the upscaler, which will then upscale your image, but is like a bit more advanced. We may actually take a look at the AMD version, because like DLSS is hard to get, and I will not be able to make a tutorial of that or publish any code on GitHub because of the NDAs. But maybe we are at some point taking a look at the AMD solution for that. Or maybe actually take a look on how this is implemented, but not currently. I have not the time to actually get myself into that big code base, or not big code base, but understanding like the mathematical details behind that. There's actually like some articles about some upscaling, and AMD kind of like take these upscaling solutions and add something on top of that. So yeah, right. Already like talking about stuff that is not related to pass 1 geometry. So now pass 2 shading. What is the second pass after we stored all the intermediate data to this intermediate or a render target? So now the last step is to compute the final color values based on the intermediate values. The nice thing is that these intermediate values are available as often as you desire. So basically what you do, there could be like a third pass in between these two passes that alter the information, but I'm going to talk about this later. And basically, yeah, the idea is that you kind of like have always access to the raw surface data within these intermediate render targets. So basically, you kind of like first in step 1 render to the intermediate render targets, and now in step 2 you are reading from the intermediate render targets. And the idea is that you can now use this information as often as you want. So you can always access to the normal. You have always access to any other computations. You don't need to redo these computations, and so you can just write your lighting computations for your different lights, for your different effects, just in a simple shader, and it can always read to that, and it always additive blends to the currently back buffer of your frame, or the current buffer that is then fed into your upscaling solution, whatever. So basically the idea is that you kind of like add all the color values to your final render targets based on these intermediate information targets, render targets. Nice thing about this is that you can group it as you desire. So you can like say, okay, I want to go kind of like brute force. I'm going to do a loop over maximum number of lights, or I do something like I have a shader which can compute light for 8 point lights, 8 spotlights, 8 directional lights, so whatever you kind of like have. And then you kind of like see, okay, I have like 9 lights in the scene, or let's say 30 lights in the scene. So you would dispatch the shader for the point light 2 times. So 2 times 8 means 16. And if you have 13 lights in there, this would mean that you kind of like waste 5 loop iterations, but you can kind of like have this dynamically. So it kind of like scales well with a multiply of 8. In this case, but you can also design it however you like. So you could also write a shader that just does computation for a single light, and maybe does, because you're just doing computations over a single light, you can then kind of like adjust your light shape, kind of like the shape that the light is covering, because like all of these passes need to kind of like cover that pixel that cover the light. And you can do this like on the light shape. If you're kind of like doing this for 8 lights, then you would kind of like need to, on the CPU or GPU side, kind of like find the bounding box that is fitting the current coverage of this light of the pixels of the screen, to then do kind of like the rendering. And this may prove as a performance increase or a decrease, but basically most of the times if you have the lights like many lights in there, they are most of the time evenly distributed, or like covering like a big area of the screen. So if you're doing this like for 8 lights, the chance is very high that it will always cover the whole screen. So at some point it might be actually like wasted computation time to actually compute which parts are covered. But in case you're actually doing this on a per light base, you can actually like for a point light, for example, just draw a bounding box around the box light, and then in the the vertex shader of the light computations, you can transform the bounding box in the right spot of the world position, and then easily you're just shading the pixel that might be affected by the light. You could also like do a more complex mesh, because a point light is well illuminating in a point, so basically like a circle. So you could like approximate the circle with a special shape and use tessellation to kind of like narrow the light computations down. But the thing is this like cheaper than doing like the computations in the pixel shader? So that's kind of like always, you need always to measure what is best for your things. But basically the idea is that you have full control on what you do. You can group as desired. You can say, okay, I do a full screen pass for my sunlight, I do a full screen pass for all of my directional light, I do some of my point lights kind of like the smart way, I do my area lights the smart way, and you can like do everything how you like. Basically, yeah, the performance depends on the coverage of the light shape. So basically, if you're doing a full screen path, but just a few pixels are affected by that light, bad, because you are kind of like having several times the computation result of 0, while just some values actually influence the image. So you kind of like would want, in this case, to actually make this a bit smaller, but this kind of like optimizations. We are just want to go the brute force with just a axis aligned bounding box that is always applied to a light. Or maybe we are actually, I'm gonna see how this is gonna turn out in our final rendering, but I think at least for point lights we are doing some optimizations there. Issue with deferred rendering: more memory and more bandwidth, because we have that many render targets. It also means that this information needs to come in. So for each pixel we are streaming in several informations from several render targets, or several resources are accessed. It's kind of like not already in the cache, and so this means that we are actually using high bandwidth. And also more memory, because we have more render targets or intermediate render targets that we need to read from. Another thing, we already talked about this, like on forward rendering, is decals. The nice thing is that you can kind of like put a decal pass between the pass 1 and the pass. Is this also called pass 1? Yeah, this should be called pass 2. You can put a decal pass between pass 1 and pass 2. So kind of like the pass 1.5 kind of like. And in this decal pass you could just do some def offsetting, so def biasing, so you kind of like add something to the def value, so that you kind of like always be sure to also overdraw. And then you would just draw the decal over your current intermediate render target. So your decal could actually influence this, and you could actually go for special texture formats for the decals. So you could kind of like add some minus and pluses, so some floating point values that go into plus and minus directions. You may actually need to encode this. So for example, like 0.5 and float means is a keep at the same, and then you would kind of like need to do some offsetting there, but you can kind of like alter the geometry informations there to kind of like lighten the color or darken the color, and do several stuff on kind of like the basic properties of the surface before you do the shading. So your decals are a bit more versatile on how they can work. Alright, this concludes the topic of deferred rendering. I'm already apologizing that there will be not soon a video in this video series, because I'm kind of like now done with all of the theory that I want to cover. Now is actually the time where I want to show you some stuff with like font shading. So actually next video in this series will be, I will explain you how I did font shading and how this all deferred rendering system that I have written comes together. But the thing is that I have currently like less time available to actually do coding, and I'm gonna go on vacation next week as well. So I'm a bit tight on schedule. It's always like bad timing, because like also our public transport is currently not working here, because they're doing some modernizations there, or not modernizations, they're just switching the stones from the train, kind of like the train bed. And the issue is that I need to take the bus now, a special bus that was just it's just there to accommodate for the train, but it's costing me like 1.5 hours more for my commute time, and this is like quite tough if you're already like working the full day. And yeah, so I don't have that many time available for do coding and doing videos. I also like do coding and also DirectX coding currently at work. which means that I'm already like 7.5 hour, or like if you actually subtract like the unproductive time, like 6 hours approximately a day coding, and also the other time like getting something from the break room, or just thinking about the software architecture is like, you are kind of like not able to do that much coding if you come home. I cannot come home and just do the whole evening from like 8 o'clock to 12 o'clock in the evening, like again coding, and also like again DirectX. And the other thing is I want to actually write a special framework. I want to write you a versatile and universal framework that you can use to also like experiment with your own real-time rendering. And I'm currently already started writing this framework, and this will contain everything. It will contain like synced out. It's not kind of like built to do production DirectX 12 work, or maybe it may at some point evolve to there as soon as I'm kind of like evolving and need more performance for my real-time rendering because our graphics get better. It may evolve into something that could be used in production, but the current goal is to build a framework which abstracts like your DirectX stuff. So basically make things a bit easier to use DirectX 12 and also real-time rendering, like serializing serializing pipeline states and all that stuff. I'm gonna do this all in a nice little library, and this currently has priority because I always like find myself rewriting all that basic DirectX stuff. So I'm gonna write this kind of like abstraction layer, this very, very broad abstraction layer. It's kind of like not abstracting at all because it's still Windows, it's still DirectX, but it's at least kind of like making things a bit more easier. Just a little util framework for DirectX 12. And I need to kind of like finish this first before I can start writing our deferred rendering system, so you can kind of like see that there is still some time to go there. I'm gonna post maybe a devlog, some updates on this framework on this channel, so that you actually have some videos. They will be quite short, but there will be at least some videos, and you can kind of like see where I'm working from, and you can also like see in which direction the framework is going, so that you kind of like also see what you can do to get kind of like to what you want. Yeah, but after this is kind of like done, we can actually go fully into real-time rendering, which I'm very hyped of because real-time rendering is so amazing. I mean, it's actually quite math intense, so you need to actually be safe in all that math. And trust me, I mean, I have written several of these techniques before, but it's not that I have written all of them. I have probably already like taken a short look and just read about them sometimes because I have like the books available. But the thing is, it will cost me several time. I always need, if in case I do something more advanced, I need to find the resources in the books that I have, find the resources, kind of like slides from NVIDIA, slides from GDC, slides from ZGraph, slides from like, most of the times it's NVIDIA slides because NVIDIA is doing a great job there on covering all the rendering techniques, but also AMD is doing that. But that's a bit more on NVIDIA as far as I know, or at least what I have read. And yeah, so yeah, it's gonna be actually also like time consuming for me, so yeah, I wanna already apologize for the lower video frequency, but we are kind of like at this position now. I may gonna do some more C++, and maybe I'm not gonna do Vulkan. I have delayed Vulkan for at least after we are getting a good chunk of work done with real-time rendering. Yeah, so I'm not gonna do Vulkan yet. I don't know how things are getting out when I'm back at university. If everything works out well, I may have the time to do a parallel Vulkan tutorial, but yeah. So just for now, be patient. The videos will continue to come, but they may not be as frequent as they are yet, or up to today. So thank you for watching. Gonna hear us, see us, whatever, in the next video. Thank you for watching. Make sure to like and subscribe, and yeah, bye.